So let's graph this. Let's graph this for a way that, let's say this is 50 centimeters, 0.5 meters high. Okay, and we have a k which is 2 per meter, or 2 radians per meter, and then omega which is 10 per second, or 10 radians per second. How is that going to look? Here is your time. Here is your y equals half a meter and negative half a meter. And let's take a snapshot of the wave at t equals 0. So when t equals 0, this disappears and we have a cosine of kx. So cosine looks like this. And I ask myself, what is the length of this wave for it to go all the way back? And I know that's when this argument grows by 2 pi. Or what is k such that when I move forward 1 lambda, I'm going to write lambda is a wavelength. What does k have to be so that when I move forward 1 lambda, I'm exactly where I started, at the same height? And that, we know, k times 1 lambda more is going to equal 2 pi, because that brings this function back to its original value. And so lambda has got to equal 2 pi over k, which in this case must be 2 pi per 2 per meter, or pi meters. So I know that this must be pi meters, and this is where x equals 2 pi meters. Now, how quickly does it go up and down? Let's take a point at x equals 0, let's say. Just stay here, and we know that this wave, which way does this wave go? We know that as time gets a little bit bigger, in order for this to remain 0, this has to get a little bit bigger too. So this maximum point will move to the right if this is negative. And then, if I'm sitting here and I'm going up and down, how long does it take for me to go up and down? And I know that that's 1 period long. And in order for me to go up and down and be right back where I was, this argument has to grow by 2 pi. So omega times 1 period must equal 2 pi. Or a period is equal to 2 pi over omega, which is equal to 2 pi divided by 10%. Or 0.2 pi seconds. And so what's my speed? My speed, I could say, is omega over k, but I could just say, look, the only formula I remember from physics is speed is equal to change in distance over change in time. And so we're talking about how long does it take a lambda to go by. As this wavelength goes by, I'm going to go up and down. So when the wave moves 1 lambda, time has to change by 1 period in order for me to be right back where I was. And so I can just put this in, and I get, it's pi meters long, the wavelength, and it goes by me in 0.2 pi seconds. And so the pi's cancel, and I end up with 5 meters per second. So hopefully what you were able to take away from this is anything that has the form of a function of kx minus omega t is going to be a traveling wave. This is traveling in the forward direction, plus omega t, it would be traveling in the negative direction. We saw that this is the natural outcome when we look at the dynamics of the forces pulling on a string, and we tried an example of a subcategory of those traveling waves, the sinusoidal function of some amplitude times cosine of kx omega t, where that is the value of the y displacement.